Hello students, welcome to the new session. Today we are going to discuss about electric field. In the last session we discussed about electric force and how the forces is acting between the two charges, three charges and as well as four charges. So we'll discuss about electric field. So what is an electric field? Generally in 11th standard we discussed about gravitational field. Gravitational field is nothing but the region around the mass which can attract or which can influence the another mass. That's we are named as gravitational field. Means if you consider Earth is having some gravitational field. If that in that particular region only, if anybody is coming, and then only it can be attracted by the Earth. So it is nothing but a region around the charge. So region around the mass, that is called gravitational field. Where we are comes to the charges, the region around the charge means we can consider a positive source means nothing but here I am considering a positive charge Q. So the Q charge. So for the Q charge there is a boundary, means there is a region which is surrounds the charge. When another charge is try to enter in that, it can influence, means it can apply some force. For example, while we are taking a charge at infinite distance means force between them is zero. When the particle is coming here somewhere else, and then only there is some force is existing between them. For example, here Q naught force is we are considering, and the distance is if you are considering like R. So then the force between the two charges we can able to write 1 by 4 pi epsilon naught Q into Q naught upon R square. 1 by 4 pi epsilon naught Q into Q naught upon R square. So here this is the electrostatic force between them. If the force per unit charge, means if I am taking the force per unit test charge, which is equal to what we can able to take 1 by 4 pi epsilon naught Q upon R square. 1 by 4 pi epsilon naught Q upon R square. That force per unit test charge we can name it as electric field. The force per unit test charge we can name it as electric field. Simply electric field, what we can say that the region around the charge or the boundary around the charge which can influence the another charge, that we can say that electric field. And electric field, how do we are measured? We can measure it force per unit test charge, where Q is called source charge. Source means which can produce just the electric field, that we can call as source charge. The charge which can test the effect or which can test the source charge, that is called test charge. Here capital Q is the source charge and small q is the test charge. So electric force per unit test charge is called electric field. So here force is vector function here. Force vector, due to that electric field also a vector function. And if you see that unit of that SI unit, we can able to take SI unit of force Newton per coulomb, or else we can also able to give volt per meter, Newton coulomb or volt per meter. Also we can able to give the unit of SI unit of electric field. So electric field is nothing but the region around the charge or the boundary around the charge which can influence the another charge. How it is? For example, you can take a magnet. I am consider this is a magnet. I am considering a magnetic substance. That magnetic substance is placed here nearer to that, then only it can be attracted. In case I am placing the magnetic substance somewhere else, is can attract? No. When the magnet can attract, when the magnetic substance is enter into the field, then only that can able to attract or that can able to repel anything, able to attract or able to repel. For example, how the action is acts. Here source charge you can consider a positive charge. I am trying to bring another positive charge, then what happen? Repulsion. In case it is the negative charge, when I am trying to bring the negative charge here, then both are attracting, repelling and as well as attracting. Means anything is happening when which is comes to a particular boundary. That particular boundary only we can call as electric field. Electric field or electric field strength. Electric field strength is nothing but electric field strength. Electric field is this, and take about electric field strength. Electric field strength is nothing but the intensity or electric field strength it is called. It is the strength of the field, electric field at a particular point. The strength of the electric field at a particular point, that we can call as electric field strength. Electric field strength at a particular point, how much it is having, that's we can take. Next, you can take uniform electric field. Uniform electric field. Uniform electric field means the strength of the electric field is remains same. The strength of the electric field is remains same at every point in the field. The strength of the electric field is remains same at every point of the electric field. That electric field we can name as uniform electric field. That electric field we can name as uniform electric field. So how we can create the uniform electric field? So here if you consider a huge amount of positive charge, at the same time the huge amount of the negative charge. So then what is happening? This positive charge can attract the negative charge. The negative charge can attract the positive charge. So then this will gives the electric field, uniform electric field. And what is this lines? So we'll discuss about that lines. The lines is called field lines, and those are having some properties also. So that we'll discuss again. So now here this strength here this is called simply uniform electric field. Uniform electric field is nothing but simply the strength of the electric field is remains constant at any point, that we can call as uniform electric field. Uniform electric field. Next we'll see the direction, how the electric field is acts. Field direction, electric field direction, very important here. Electric field direction, because already we mentioned that which is a vector function. Let's see here. Here I am considering a positive charge. For a positive charge, the electric field is act away from that. Means you want to calculate the field strength at a point P. The field strength at a point P. Then field strength is acting away from the charge. The field strength is acting away from the charge. Away from the charge. Means you take a positive charge Q, and at the P point what is the electric field? At the P point the electric field is E, but in which direction? In this direction. In this particular direction, means which is away from the, for a positive charge the electric field is acts away from the point, away from the charge. Whereas comes to the negative charge, if you consider here a negative charge, for a negative charge the electric field will act, the electric field which can act towards the charge, towards the charge. For positive away from the charge, for negative towards the charge. Positive away from the charge, negative towards the charge. Very important. What is the field direction for a positive? Field direction for a positive charged particle is away from that. The field direction for negative charged particle is towards. Field direction for positively charged particle is away from that. Field direction for negative charged particle is towards that. Towards, which is acting towards. This is for away from that. Very important. For a positive, please note on that point. For a positively charged particle, for a positive charge, the field direction is away from the charge. The field direction is away from the charge. Away from the charge. For a negative charge, the field direction is towards the charge. Towards the charge. For positive, away from that. For negative, towards. Positive, away from that. Negative, towards. Away towards. So now this positive charged particle, while we are keeping in uniform electric field. So here uniform electric field means what I did here, I am considering a huge amount of positive charge, huge amount of negative charge, then that creates an uniform electric field. In uniform electric field, already I mentioned what is the direction of the electric field. The direction of the electric field away from the positive charge towards the negative charge. Away from the positive charge towards the negative charge. For example, if you consider we put a positive charge, nothing but a proton, if you put in a uniform electric field. Uniform electric field means no need to write every time this positive negative. Just you can mention some lines parallel to each other and the arrow marks like this. So this is uniform electric field. But just you have to imagine here there is a huge amount of the positive charge. You have to imagine yourself. There is a huge amount of positive charge. From positive charge, field lines are moving away. And here you can imagine there is a huge amount of negative charge. For the negative charge, the field lines are coming towards. Like that you have to imagine. But every time you are not able to draw this. Just now here which amount of charge you have? Huge amount of the positive charge. Here huge amount of the negative charge. So that's why the field lines are taken from positive to negative. Here what I am doing, I just put a positive charge here. Which charge? Positive charge. Can you imagine in which direction the positive charge is moving? Can you say that? In which direction the positive charge will move? In which direction the positive charge will move? Can anyone say that? In which direction the positive charge will move? Yes, the positive charge is moving along the field direction because here we said that there is a huge amount of negative charge. So here it is the positive. Positive, positive, both are enemies. Nothing but positive repel positive. And positive negatives both are friends. Nothing but the negative can attract the positive. So that's why the positive charged particle is moving along the field direction. Along the field direction. Write down here a point. Write down a positive charged particle. A positive charged particle is placed in uniform electric field. A positive charged particle is placed in uniform electric field. Then the particle is moving along the field direction. Then the particle is moving along the field direction. A positive charged particle placed in uniform electric field, then that is moving along the field direction. Along the field direction. Let's see, one more we'll see here. Same condition, same uniform electric field. But I'll try to put a negative charge here. Negative charge, Q, minus Q. So then which direction it can move? In which direction that can move here? Which side? Yes, it can move in opposite to the field direction, because here we have to imagine there is a huge amount of positive charge. At the same time here there is a huge amount of negative charge. Again negative, negative, enemies. Negative, positive, friends. Means this negative amount, it can be attracted by the positive, repelled by the negative. Means what we can say that the particle is moving towards the positive charge, towards the positive. Nothing but a negative particle or a negative charge is placed in uniform electric field. A negative charge is placed in uniform electric field. Then it is moving opposite to the direction of the electric field. It moves along the direction opposite to the direction of the electric field. So here one more question there is a chance to ask. For example, if they mention electric field strength is E and the charge is Q, mass is M, mass of the charge. What is the mass of the charged particle? Mass of the charge is M. Then what about the acceleration of the charged particle? What about the acceleration of the charged particle? Acceleration of the charged particle. If they are asking acceleration of the charged particle, let's see what are the forces acting on that. What are the forces acting on that? Here the particle is accelerate because of the electrostatic force. Then electrostatic force equal to simply mass into acceleration. Electrostatic force equal to mass into acceleration. According to the definition, what we can able to give? From the definition, we can say that F is equal to E into Q. Is it possible to write or not? Yes. From here, E is equal to F by Q. Then F is equal to E into Q, na? Yes or no? Yes. F is equal to E into Q. That means if we are put the value of F here, so then how much you are getting? Simply F is equal to MA, or else EQ is equal to MA. Then acceleration of the particle E is equal to EQ upon M. Acceleration of the particle A is equal to EQ upon M. That is the acceleration of the particle. Which direction? Along the field direction. In case if we are taking here, which direction? Opposite to the field direction. Opposite to the field direction. That is the acceleration of the charged particle. Very, very important here. So again we can discuss detailed. See here, a charged particle is placed in uniform electric field. Which direction that is moving? Along the field direction. What is the acceleration? EQ by M. A negatively charged particle is placed in uniform electric field. Which direction that is moves? Opposite to the field direction. What is the acceleration? If you are calculating, that is moving opposite to the field direction. Magnitude of acceleration is equal to same. Simply EQ by M. But what about the direction? The direction is opposite to the field direction. Opposite to the field direction. So we'll take one small problem. See here, very small problem. Here we'll solve the problem, but before that we will discuss a small concept here. That is a null point. Which point? Null point. Null point means the point at which the net electric field is zero. The point, null means zero. The point at which the net electric field is zero, that point we can say that null point. The point at which the net electric field is zero, that is called null point. See here. So in case if I am considering two positive charged particles, two positively charged particles. One is Q1 and other one is Q2. Plus Q1 and as well as plus Q2. At which point the electric field is becomes zero? That's we need to identify. At which point the electric field is becomes zero? One positive, one positive, two positives. So let's see here. What I am considering here? I am considering a point left side of Q1. Left side of Q1. What is the electric field due to the first charge? So generally we know that it is a positive charge. Yes or no? Yes, it's a positive charge. For a positive charge, what about the field direction? Away from the field direction, na? Yes. So here it is giving E1 field direction, away from that. Away from that. Next, take the second charge. For the second charge, what is the field direction about point P? Again positive, so that's why again it is also acting away from that. Away from that. If two are acting in the same direction, is it possible to zero? No. When that is possible to 0, those must be acting in opposite side. Opposite side. That means here in the left side there is no null point. Left side of the charge of Q1 there is no null point. Let's check right side. Right side means here I am considering the point B. Here I am considering point B. On point B means what about the Q1? Means field due to the Q1. Positive charge, nothing but away from that, positive charge away from that. What about the field due to Q2? Again away from that. Away from that. So here also E1 and E2 are acting in the same direction now. E1 and E2 are acting in the same direction. So that's why left side field not 0 and right side also not 0. Left side field is not equal to 0. Right side also field not equal to 0. Let's check here. This is the point P, Q, R. So about this point, what is the field direction? Away from that, E1. Here field direction. Away from that, E2. Is it possible to 0? No. For possibility 0, must be opposite to each other. Opposite to each other. Either way, here also not becomes 0. Let's check here. Let's check here. This is E1. This is also E2. Is it possible to 0? No. Resultant is acting in this side. Then last possibility between the charges. Take here P, Q, R, S, T. At this point. At this point, what is the field due to Q1? In this side. What is the field due to Q2? In this side. Yes, that means their field becomes 0. At what point? Where the field is becomes 0? For the like charges. For the like charges where the field becomes 0, the field becomes 0 between the charges. Between the charges. Line joining and between the charges. Can you write it? Statement? Yes. For like charges. For like charges. For like charges, the null point is presenting between them. Presenting between them. Where it is located? Between them. Between them. See here once again. Here about the both fields are acting here. Away from away. And here also away, so that's why here not 0. Here not 0, here also not 0. Here 0 because both are acting in opposite side. Opposite side. So let's see. We solve here the equation of null point. For example, same I am considering same situation. I am not changing the situation, but I am giving the just the distance between Q1 and as well as Q2 is R, which are capital R, and the null point is at a distance x from the Q1, at a distance x from the Q1. So now we'll try to get the null point here. What is the field direction due to Q1? Due to Q2? That means the net field must becomes 0. So that is equal to field due to the first charge is equal to field due to the second charge. Field due to the first charge is equal to field due to the second charge. Then write E1 value. E1 is equal to 1 upon 4 pi epsilon naught Q1 upon x square, because at a distance of x, which is equal to 1 upon 4 pi epsilon naught Q2 upon how much distance? R minus x. R minus x whole square. Just cancel 4 pi epsilon naught, and better to send this R minus x whole square here. R minus x upon x whole square. I am doing here this R minus x I am sending here. This R minus x upon x whole square is equal to Q2 upon Q1 is equal to Q2 upon Q1. Just to remove the squaring, then you can get here square root now. That means R minus X upon X is equal to square root of Q1 upon Q2, under root of Q1 upon Q2. Then we can able to write R by X minus 1 is equal to under root Q2 upon Q1. 1 you can send there. Then the 1 becomes as minus becomes as plus Q2 by Q1 plus 1. Then X is equal to R upon under root Q2 by Q1 plus 1. Q2 by Q1 plus 1. So this is the location of the null point. Location of the null point when two charges are like. Two charges are like. So we will see when two charges are unlike. When two charges are unlike, we'll see where is the location of the null point. So we'll take one like charge and one unlike charge. Means nothing but one positive charge, one negative charge. Let's check fast. Where is the location of the null point? You can take between them because for like charges between for unlike we will check. What is the field direction due to the positive charge? The field direction due to the positive charge is away from that. Very good. E1. What is the field direction due to the negative charge? Away from that. Array, दोनों एक ही side act हो रहे means both are acting in the same direction. Is it possible to become 0? No. That means null point is not locates between them. Let's see here. Field direction about this, away from that. Field direction about this, towards that. E2, E1. Is it possible to become 0? Here also, no. Let's see here. The field direction about the positive charge, away from that. The field direction about the negative charge, towards. Is it possible to become 0? No. So, middle, between them not possible. And upper side not possible. Downside also not possible. Let's check right side or left side. I'm taking here. At this point. What is the field direction about the positive charge? Away from that E1. About the negative charge? Towards. Yes, here both are opposite. That means here there is a possibility of null point. Here see. Here also. For E1, yes, away from the charge. E2, towards. That means here also there is a chance of null point. For like charges, where the null points locates? Between them. For unlike charges, it is presenting either side. Null point locates either side of charges. And one more important thing, which is the null point is nearer to the smallest magnitude. Okay, we'll take the formula where it is taking. Here I am considering plus Q1 minus Q2 plus Q1 minus Q2 are separated by distance R, and null points where either side of the charge. Q1 minus Q2. Then here I am considering, means it is at X distance and this is R distance. X distance, R distance. This is the null point. For example, if you are imagining. What is the field at this point? The field at this point is about the 1, away from that, about the 2, towards that. That means at that point net electric field is equal to 0. That means E1 is equal to E2. E1 is equal to 1 by 4 pi epsilon naught Q1 upon x square. E2 1 by 4 pi epsilon naught Q2 upon R plus X whole square, plus X, because either side of that, from here to here R, here to here X, R plus X whole square. 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, cancel. This R plus whole square send here, R plus X by X whole square is equal to Q2 by Q1. Then just to take the, remove the square, then you can get the square na, root na. Yes, R plus X by X is equal to root Q2 by Q1. Then R by X plus 1 is equal to root Q2 by Q1. Just send minus 1 there, plus 1 there. That becomes as minus Q2 by Q1 minus 1. Then X is equal to R upon under root Q2 by Q1 minus 1. For like charges, plus 1. For unlike charges, minus 1. So that is the formula to find the location of the null point. And one important point, note down. The null point is always nearer to small charge. Smaller charge in magnitude. Smaller charge in magnitude means in this, for example, it is Q and that is 2Q. It is locates to nearer to small q. Yes. So that is about the null point. So we'll see one problem here. There is a there is a problem here. See, P point is here. Q charge is separated at a distance D. Minus 4Q is separated at a distance 2D. Plus 9Q is separated at a distance D plus D plus D 3D. Then what about the electric field at point P? Electric field at point P. So at point P, first I am taking the electric field due to Q charge. Field due to Q charge. This Q charge is separated at a distance D. The field direction is away from that. I am giving the number E1. E1 is equal to what we can able to write 1 by 4 pi epsilon naught Q by D square. Q by D square. Give it is equation 1. Next, take about 4Q. About 4Q. Minus 4Q actually. How much distance? 2D distance. Minus means electric field is acting towards na. That is I am giving E2. E2 is equal to 1 upon 4 pi epsilon naught. How much? 4Q by how much? D plus D, 2D. 2D whole square, nothing but 1 by 4 pi epsilon naught 4Q upon 4D square. So what is the value you got? E2 is equal to 1 by 4 pi epsilon naught Q by D square. If you want to mention, you can mention minus. The minus represent opposite side. No problem. You can take because already we mentioned direction. Let's see about this one. About minus plus 9Q. Plus 9Q is at a distance D plus 9Q. Plus 9Q. What about the field due to this? In this direction, E3. Now try to get the value of E3. E3 equal to 1 by 4 pi epsilon naught. How much? 9Q by how much? 3D square. 3 square. 3D whole square. The value is goes to 9Q by 9D square. 9 cancel. That means how much you are getting? 1 upon 4 pi epsilon naught. Let's see at point P. E1 is acting. How much? E1 is equal to 1 upon 4 pi epsilon naught. E2 also 1 upon 4 pi epsilon naught. E3 also 1 upon 4 pi epsilon naught. Q by d square, Q by d square, Q by d square. So this is, I am taking E. You can give something here is equal to E naught. This is also E naught. This is also E naught. One E naught is acting like this. Another E naught also acting like this. This is due to plus Q. This is due to 9Q. And this is due to minus 4Q. Then what about the net charge? The net charge is equal to 2 E naught minus E naught. That is equal to E naught. E naught. In which side? Left side of Q. Left side of Q. So that is the one value. Let's see one more problem. What is the electric field at point? There is plus 3Q and here minus 4Q. So let's take the direction of the electric field at point P. This is positive charge. The field direction is this. This is negative charge. Then field direction is this. Means both are perpendicular to each other. But first try to get the magnitude. How much distance? D distance and as well as D distance. Let's write E1 is equal to 1 upon 4 pi epsilon naught 3Q by D square. 3Q by D square. Next E2 is equal to 1 upon 4 pi epsilon naught 4Q by D square. No need to mention the magnitude direction because already we are mentioned that is going here. So that's why again don't take minus. Now these two are, how these two are? Perpendicular to each other. So that's why what I am doing here, this 1 by 4 pi epsilon naught Q by D square I am considering E naught. Nothing but this value is goes to 3 E naught and this value is goes to 4 E naught. 1 upon 4 pi epsilon naught Q by D square I am writing as E naught. Why? For our comfortability here. Now these two are perpendicular to each other. Then the net or the resultant is equal to under root 3 E naught square plus 4 E naught square. 3 E naught square plus 4 E naught square. 9 E naught square plus 16 E naught square. That is 25 E naught square. That is equal to 5 E naught. Direction is in this side. Direction is in that particular side. In case if they are asking a vector notation, then you can write the vector notation for that. Simply plus 4 E naught I cap minus 3 E naught J cap minus Q downward side, downward direction. Okay, let's see. Here we have electric field lines. Electric field lines. What are that electric field lines? The electric field lines are the imaginary lines are drawn from the unit positive test charge. Drawn from the unit positive charge. So means here field lines are imaginary lines. It's not real. Those are imaginary lines. For example, if I am considering a positive charge, for a positive charge the field lines are away from that. For a positive charge the field lines are acting away from that. Means the field lines are starting from the positive charge. Starting from the positive charge. And the field lines are ends on the negative charge. So first of all you can see that what are the field lines? What are the field lines? Field lines are, electric field lines are the imaginary lines. Imaginary lines are drawn from a unit positive charge. Drawn from the unit positive charge. If we are taking for a positive charge, electric field lines are starts from the positive charge and ends on the negative charge. Where these are ends? Those are ending on the negative charge. Ending on the negative charge. Starting from the positive charge, ending on the negative charge. Field lines starts from the positive charge, ends on the negative charge. And one more important point. Some points are there, properties are there. Let's see what are the properties of field lines. First property, field lines are starts from the positive charge. Field lines are starts from the positive charge. Next, the field lines are ends on the negative charge. Where those are starting? Those are starting from the positive charge. Where those are ending? Those are ending on the negative charge. Next, let's see the third point. The field lines are never forms the closed loops. Means you can see here, for example, there I am taking a positive charge, here I am taking a negative charge. The field line you can take like this, like this, like this. But here the field lines are never forms the closed loop. Field lines are never forms the closed loop. You can able to write. So starting from the positive charge, ending on the negative charge. A closed loop means if you are taking the magnet, for the magnet, the magnetic field lines south to north inside the magnet, outside the magnet north to south, means those are forming the closed loop. But field lines or electric field lines are not forming like that. These are never forms the closed loop. Next, one more point. The point at which the field lines are closer, then electric field strength is more. For example, I am considering here a charge particle. This charge particle is releases the field lines like this. So here I am considering point 1 and here I am considering point. Among point 1 and point 2, where you have the maximum field? Where you have the maximum field? You have the maximum field at point E1. E1 is greater than E2. E1 is greater than E2. Nothing but where the field lines are crowded, their field strength is more. Where the field lines are wider means away from them. So that is their field line where the field strength is less. Fields wider, field strength less. Crowded, field strength more. What are the properties? Once see that field lines are starts from the positive charge, ends on the negative charge. Here never forms the closed loop. And where the field lines are crowded, their electric field strength is more. Where the field lines are wider, their electric field strength is less. Next, one more property. The field lines never intersect each other. If the field lines are never intersect each other, for example, here I am considering a positive charge and here I am considering negative charge. Then the field lines are going from directly from positive charge to negative charge like that. So those are never intersected. Two field lines are never intersect each other. If they are intersecting at the point of intersection, the field is having two different directions. At the point of intersection, the field will have two different directions. So once again see here, positive to negative. So here field lines never intersect each other. Field lines never forms the closed loop. At the same time, field lines never intersect each other. If they are intersecting at the point of intersection, the field is having two different directions. But that is impossible. That is impossible. So once again see the properties. What are the properties we have to know what we have discussed? First property, field lines are starts from positive charge, ends on negative charge. Next, field lines never forms closed loop. Field lines never forms closed loop. Next, where the field lines are crowded, their field strength is more. Where the field lines are wider, field strength is less. Next, field lines are never intersect each other. Field lines are never intersect each other. If they are intersecting at the point of intersection, the field is having two different directions. And this may use the uniform electric field here. And if you are taking the field lines, it may forms like this also. So this is negative charge. Then we can able to draw the field lines in this way also. These are the properties of field lines. So let's see the situation here. The electric field is acting vertically upwards. And here I am considering a positive charge, and the presence of gravity also is there. Gravity is acting downward direction. Then electrostatic force will act. What is the direction of the electric field? This is the direction of the electric field. And positive charge particles also try to move in this side. So if Fe is equal to mg, if Fe is equal to mg means electrostatic force is equal to weight of the particle. So then the particle at rest condition, particle at rest means this is only we can give Eq is equal to mg, then particle at rest condition. In case if E is electrostatic force is greater than weight of the body, electrostatic force is greater than weight of the body, then the particle starts to accelerate in the direction of the more force na. This force is maximum, so then the net force acting on the body is equal to electrostatic force minus weight of the particle. Electrostatic force minus weight of the particle. Here the acceleration of the particle is Eq minus mg upon m. Eq minus mg upon m. In case mg is greater than Eq, mg is greater than Eq, then equation becomes mg minus Eq by m. Like that we can able to take. Next, for example, here one more condition what I am considering. Here I am considering a uniformly charged, uniform electric field under the absence of gravity. Here I am not considering the gravity, but what I am saying here, this is the field direction. Field direction, electric field lines. So here what I am saying here, this is the positive and this is the negative. At the positive, from the positive plate I am releasing the proton. From the positive plate I am releasing the proton, and the distance is d here. Distance is d. And the positive plate I am releasing the proton here. And from negative plate I am releasing the electron from the same type. From positive plate proton, from negative plate electron are releasing at the same time. So then which one reaches the opposite plate in short time? Which one reaches the opposite plate in short time? That is the question to us. So to get the time, so we are releasing means the initial velocity is 0. Initial velocity of both is 0. Then those are getting accelerated, then V is equal to U plus AT. Then V is equal to simply AT. A stands for acceleration, T for time. And those are traveling a d distance. So first of all, you try to get acceleration of the each one. Acceleration of the electron. Mass of the electron into acceleration is equal to E into means generally what we are taking, electrostatic force is equal to EQ is equal to M into A. So E into charge of the electron E, mass of the electron ME, and acceleration of the electron AE. That is nothing but the acceleration of the electron is equal to simply E into E by M. E into E by ME. Similarly, acceleration of the proton, E into E by MP, mass of the proton, mass of the proton. And how much distance they traveled? D distance. Then the distance traveled by them is equal, D is equal to UT plus half AT square, but U is 0, then distance traveled by them half A T square, half A T square, then T is equal to 2D upon A, under root 2D upon A. So here, see one thing here, the acceleration is inversely proportional to mass. Among those, which one is, means acceleration is inversely proportional to mass? Acceleration is inversely proportional to mass. Which one is having more mass? That one is having less acceleration. We know that the mass of the proton is greater than mass of the electron. Mass of the proton is greater than mass of the electron. That means acceleration of the electron is greater than acceleration of the proton. Acceleration of the electron is greater than acceleration of the proton. So here time is inversely proportional to acceleration. Square of the acceleration. Which one is having more acceleration? That is taking more time. More acceleration, less time. The time of electron is taking less than time of proton. See here, mass is inversely proportional to acceleration. So mass of proton greater. So that's why mass of electron greater. Acceleration of electron greater. Acceleration is inversely proportional to time. Acceleration is greater for electron. So that's why which is taking less time. Among electron and proton, electron will reaches the plate first.